This video covers one of the topics in chapter 6. It's the one that underlies all of the exercises at the end of the chapter. And there are several examples in the book, but I'm going to go over two examples here. One is a toy example just to show you how the method works, and the other is a little more complex and realistic example. And the examples both cover what I'll call frequency severity modeling, which is a class of problems where you have two kinds of uncertainty. One is uncertainty about whether something will happen, and then when it happens, how big is it? So how often it happens is a frequency uncertainty, and then the size of what happens is known as the severity function. And the terminology is adopted from the insurance industry, where the entire insurance industry is problems like that, where there's a frequency of making claims and then there's the severity of how big the claims are. But you'll see it applies to a whole set of similar problems. So the toy example, which is not meant to be realistic, just meant to show you how it works. Let's say that you are making sales and you're making 20 sales calls to different people. So we'll number the people 1 to 20. And you want to model how much total sales you'll make when you try to sell to 20 people. And let's assume that there's a probability of making a sale of 30% on any given person. So we could model that with a Bernoulli distribution. We call people, and there's a 30% chance that each one will make a purchase. Just copy that down. That's the sale, whether there's a sale. Potential sale amount. We'll make it a log normal distribution. And I'm going to assume that the average sale amount is 100 with a standard deviation of 50. So let's just see what that looks like. That's a skewed distribution. The sales could be as high as 300. Most of the time they'll be less than 100. And let's just assume that that's the potential sale that we make at each person. And that's also uncertain. The actual dollars of sales, we can multiply the two together, because when the sale is 0, we won't be counting the potential sale amount. And when the sale is 1, we will get whatever that simulated sale amount is. And what we're interested in is the total dollars collected. That's the sum of D2 to D21. And I will make that an output. So just to see how this is working, I randomize it. Notice that I have everyone has a potential sale amount, but what's shown here are only, looks like 7 sales were made by these amounts. It added up to 762. I'll get different numbers of sales each time, different amounts. These are just the totals and showing how it varies. Now, in most of these problems, think of an insurance company that insures tens of millions of people. Building the spreadsheet, you don't want to model each individual person, whether they make a claim and how big it is for every person individually in the spreadsheet. It'd be nice to have a shorthand version. Well, there is a shorthand version we could try here. The number of sales out of 20, if these are Bernoulli distributions, each person's an independent trial with a 30% chance of making a sale. We can model the number of sales out of the 20 with a binomial distribution, where we have 20 people and the probability of a sale for each person is 0.3. Now, as I press F9, you can see how the number varies. On average, 30% of 20 people would be 6 people. Sometimes we don't usually get 6, we get more, we get less, but we get 6 occasionally. And the amount of each cell is the log normal with a mean of 100 and a standard deviation of 50. So a quick way to do this would be labeling it wrong, because this is the wrong way to do it, but it's sure it looks simple, would be take how many cells there are, we're simulating that in G3, and multiply it by the cell amount, which is in G4. And let's just make that an output the wrong way. Now what we want to do is run a lot of simulations, so let's make it 10,000 of them. Use the same random seed, run the simulation, and let's compare the results. Let's try to overlay what we know is correct in G1 with our shorthand version, which is in G6. One thing you'll notice is if you look at the mean on the right here, 600, 599, the means are almost the same. Take a look at the standard deviations though. The wrong way, $377, $238 the standard deviation from the right way. You can see the red is more spread out than the blue. A much easier way to actually visually see this is to go to box plots. The wrong way is on the left, the right way is on the right. Notice the left more spread out, the extremes are bigger, the middle 50% is bigger. The line in the middle, the mean, is almost the same. So for estimating the mean amount, the average amount that we will collect from the 20 people, doing it the wrong way is fine, it gives us a right answer. But the uncertainty, the likelihood of having a number, let's say bigger than 1,000, is sizable. We do it the wrong way, but the right way, it's almost impossible to happen. So there's something going wrong with the way this is done. And the thing that's going wrong is that by simply making our model this small, we're multiplying the sales amount, the number of sales, by a simulated sales amount. If there are 6 sales, they're each going to be $90. If I press F9, I have 4 sales, but they're each at $88. In reality, what's happening is each sale of the 4 probably has a different amount, and that's what's shown on the left. You can see each of the sales that are being simulated here, and the reason they don't match is that the number of sales from the binomial here is not linked to each of the individual sales. So in each iteration, right now, it's showing 3, 7, 9 sales on the left, 4 on the right. 6 sales on the right, there are 5 sales on the left. They're not tied together, but when you run 10,000, it kind of evens out so that that discrepancy that you're seeing visually doesn't matter. The point is, on the left, each sale is for a different amount. This little highlighted model here gives me the same average amount, but the uncertainty is wrong because it's attributing the same amount to every sale that's made. There is a right way to do the short model here. Call it correct, but it's a short correct model. The actual G1 is a correct amount as well. And this is to use something called the risk compound function. Designed specifically for this purpose, it wants 2 entries. It wants to know a frequency distribution. How often does it happen? Well, we've got that in G3. And it wants a severity distribution. When it happens, how big is it? That's in G4. So the only difference between this cell, which I will make an output, and this cell, which is wrong, here I'm multiplying the 2 together. Here I'm using a special function, the risk compound. And what the risk compound does is it looks at this frequency distribution and then randomly picks from the severity distribution a different amount for each of the frequencies that are simulated from G3. So unlike multiplying together, where here all 5 sales would be for $104, if there are 5 sales, each of them has a different amount drawn from the severity distribution. And so we run this now. Simplest way to look at this, let's go to a trend chart, look at the modeling each individually, our short model that's wrong and our short model that's correct. If you compare the left and the right, the total collected from the 20 households modeled individually and the use of the risk compound function look pretty much identical, the left and the right. The middle one is the one that's off, that's done wrong. It's far too much uncertainty because it's assumed that every sale is for the same amount. So if you have a large amount of sales, they're all large amounts. If there's a small amount of sales, a small dollar amount, every sale's for a small amount, whereas the left and the right allows each sale to have an individual amount that's different, draw from the severity distribution. So risk compound function is the way to correctly model frequency severity. The only thing from the short model that's correct is the average that you get from this cell will be very close to the right average, but the range of variability is all off. So you can build a very simple model. I mean, this is a 3-line model. How many sales? How many sales? What does the severity distribution look like? Put the two together using the compound function. 3 lines handles the model that's on the left. In fact, if you had 1 million households, you only need 3 cells to build the same model for 1 million households, whereas on the left, you'd have to write out all 1 million. So it's a very quick way of getting a simple, short model that captures a lot of information. So let me go to my more complex example. I downloaded the actual departure information for flights from Anchorage in January 2019. It shows all of the flights from Anchorage in that month. It shows what airline it was, the flight number, where it was going to, the date, the scheduled departure, the actual departure, the scheduled arrival time, the actual arrival time, how late it departed, negative numbers mean it departed early, how late it arrived, negative numbers means it arrived early. Then I created some columns. Is there a late departure? If the number in J is greater than 0, I said it's 1, means that it is a late departure, otherwise 0. So the negative sign, it's not a late departure. This one was 47 minutes late, it was late. And then in the next column, I put an if statement that if it's a late departure, let me know how many minutes late. Otherwise, leave the cell blank. And the reason for leaving it blank rather than putting in a 0 is I'm going to try to look at I want to look at the distribution of how long the delays are. And if it has zeros in there, it's counting the zeros. I want to know with the severity distribution, you want to know when a sale is made, or when an event happens, how big is it? So when it's late, how late is it? Not is it late or not? That's what the frequency distribution picks up. So column L is telling us whether the departure is late or not. Column M is only showing when it's late, how late is it? And the same thing for arrival. If the arrival departure is great, late time is positive, then make it a 1, otherwise a 0. And then if it is late, how late is it? That's what's shown as the number that's in column O. Okay, so this, and there's interesting data. You can download this, I think, every month, monthly data for the last, I don't know, 30 years, something like that. They're pretty big files because they download the entire country at once. I just pulled out the ones that departed from Anchorage. You could, of course, narrow this down and say, well, let's just look at Anchorage to Seattle and not Anchorage to anywhere else. I'm just lumping them all together here. You can look at the dates and say it doesn't matter maybe what the weather's like on those days. So I've hidden that. I haven't modeled all that, but it's capable of being modeled. You might look at the hour of the day because departures may vary over the day. There may be some kind of seasonality throughout the day. I'm not looking at any of that. I'm just looking at how often are there delays and how long are they. And the possible use of this is you might be interested in knowing what the total number of minutes is in a January of delayed time, because it affects things like airport services, how many restaurants you need, how long they have to be open, gate space, sitting space for people, because when flights are delayed, they need more room to sit. The airlines would be concerned about the total minutes of delay because it costs them real dollars in many different ways. So there's a lot of potential uses of trying to model the total minutes of delay that occur each month. And you might want to compare it for different airlines. But right now, I just want to get a model that models the total number of minutes of delays. So what I've got over here are a number of calculations. The fraction of departure delays, I looked at column L, my frequency cell, 0 or 1. Is it delayed? Count how many ones there are in that column. There are 1,423 flights here. So it's about 19% had departure delays. Count how many had arrival delays. That was about 25%. Column S shows a simulated frequency. If you have 1,423 flights and each one has a 19% chance of being delayed on departure, S1 simulates the number of delayed flights out of the 1,423. This simulates the number of delayed arrivals out of 1,423 flights. So then what I did is I took column M, the size of the departure delay, and this is also why it's important to have the blanks in there. When you go to fit a distribution, notice this that comes up, this is exactly what you want. There are one or more blank cells, they will be ignored. If there were zeros, they would not be ignored. They would be used in the distribution. We're interested in the severity of the delay when a delay happens. Whether a delay happens or not, that's what the frequency distribution is for. So it's exactly what we want, it to be ignored. The log normal distribution comes out to be the best fitting. But I'm not going to use it because notice if you look at the mean of the actual data and log normal, 32 minutes versus 52 minutes, and a standard deviation of about 40 minutes versus 224 minutes, that's quite different. If you try the exponential distribution, the picture looks a little better to me. It's not going to have that big spike at very small numbers. It's not quite high enough, but it's closer. Look back at the log normal, where the spike is way higher. So the log normal attributes a lot more flights that would have very, very short delays. I should mention, by the way, for the actual late departure times that are calculated by the Bureau of Transportation Statistics, they count any flight that takes off within 15 minutes of its scheduled time as actually on time. I've deviated from that here. I've assumed if there's any positive delay at all, it's delayed, but you could easily have changed that to 15 minutes if you want. When you look at the exponential, the picture looks better and the numbers look a lot closer. The mean 32 versus 32, almost exactly. Standard deviation's off a little bit, 40 versus 31, but not as far off as the other was. So I'm going to use the exponential here. And that's what I put in for the departure distribution. When I did the arrival distribution, I also did not choose the best one. I didn't actually choose the second best either because, as we know from prior examples, when you start changing the distribution and you're trying to compare them, you can get artificial results just because the distribution shape changed. The exponential was pretty good for this one as well, so it was the third on the list, so I chose the exponential for both. Now, the wrong way of doing the calculation would be to simply multiply the number of flights delayed times the severity distribution. And for arrivals, do the same thing. And what I'm calculating here is the mean of the total minutes that are modeled that way, the 5th percentile, the 95th percentile. A correct way to do this would be to use the compound function, the risk compound, where you use the same entries. You're simulating in S1 the number of delayed flights out of 1423, and the severity distribution, R3, but the compound functions allowing each of the delayed flights to have a different amount of minutes delayed, whereas the wrong calculation assumes every delayed flight will be delayed by exactly the same number of minutes. And then I'll look at the mean of that and the 5th and 95th percentile of that. And just for information here, the total number of minutes, since I have 0, 1 cells for whether it's delayed, I can just multiply some product of L times M to get the total departure delays, and this one, O, N times O, to get the total arrival delay minutes. So these are actuals. And let me go ahead and run this. If you compare the means first, for departure delays, 8,614 minutes for a month of January. Doing it the correct way is 8,461, not much different. The actual is 8,645, so they're all pretty close. The mean is being estimated correctly whether you do it from the data. Of course, remember we're simulating, so we shouldn't match the actual number exactly. The simulation's basically saying, well, if we simulate 10,000 Januaries, on average, what do they look like? It's not that different from what the actual number was for this particular January 2019. But they're all roughly in the same area. If you look at the arrival delays, notice the arrival delays are longer in all 3 circumstances, because a lot of other things can happen once a flight is delayed in terms of whether it arrives late. In fact, as we saw from the frequency, 19% of the flights are delayed on departure, but 25% are delayed on arrival. So there's lots of flights that are delayed when they arrive, but they took off on time for all sorts of reasons. So the means all look very close. 10,491, 10,409, 10,520. They're all fairly close. Oh, actually, these are the ones I should be comparing. These 3 cells, the means of them, 8607, 8614, 8645, or these 3, this, and this. Again, they're all close. But look at what's different. The confidence interval, the 90% confidence interval done the wrong way would be from 668 to 25,000 minutes. The correct confidence interval is more like 7,500 to 9,800, much narrower interval, much narrower. And the reason is, again, doing it the wrong way, we're assuming every single delayed flight has exactly the same number of minutes of delay, whereas some delays are short and some delays are long. And when you have on the order of hundreds of flights being delayed, it matters that some are long delays and some are short delays that kind of average out, and you get a much narrower confidence interval. For the arrival delays, the confidence interval here ranges from 820 to over 30,000. Doing it the correct way, the range is only 9,300 to about 11,800. So much narrower confidence interval again. So if all you're interested in is the averages, then doing it the wrong way is fine. They'll give you a approximately the right average. Just multiply how many delayed flights there are by what the average departure delay is. In fact, you don't really need to be running this simulation at all. If all you're interested in the average, you sort of don't want to run simulations, because in the average, just put down what is the average delay, what are the average number of delayed flights, multiply the two together, that will give you the average total number of minutes of delay. If uncertainty matters, though, averages are not good enough. So the point is, when you want to model uncertainty, you want to know not just on average what the delays are, you want to know what they can range, how much can they vary. If you're thinking about sizing the seats in an airport, you don't want to size it so that on average you have the right number of seats, which means half the time you probably have empty seats, too many seats that you put in, and the other half you're running short of seats, which can be a problem, as you've seen in many airports where they don't seat that size seating space right. Go to O'Hare sometime, there's lots of delays, and at O'Hare there's not enough seat space most of the time. So uncertainty means you want to know what happens in those extremes. You want to know, maybe not the total range from minimum to the maximum, but you might want to say, well, I want a 90% confidence interval. I want to plan for that potential range. Insurers are not, they are concerned with what their average payout will be, but they're also concerned about what they need to set aside. They need to be prepared to pay out claims of, let's say, at least 90% of the time they want to be able to cover the claims, so they're interested in the 90th percentile of the distribution. So when you're interested in uncertainty, you're interested in what that distribution looks like. So you're interested in things like the confidence intervals and not just the mean, and that's why you need to use the compound function, because otherwise you get the very misleading confidence interval, far too wide, because it's not accurately measuring it. The great advantage, though, these are extremely small models that you can build that can handle a lot of flights. So we could easily change this to 1,000 flights. And if you want to actually model the left-hand side if you want to make it 10,000 flights instead of 1,300 or whatever that number was, you'd have to add rows for each of the flights. Whereas on the right, all we have to do is essentially use this part and this part. That's the size of the model. You can change the number of flights to any number you want, and the model doesn't have to get any bigger. So it's a very efficient way to model very realistic and large problems. Okay, the book contains other examples, and the exercises will give you, even if you're not doing them all, I would read through them just to see the array of different kinds of problems that are amenable to frequency severity modeling.